Okay, thank Tom for the introduction and thank the committee for the invitation. I'm Yan Liu from Caltech. Today I'll be giving an overview of some of the work we have done to focus light inside opaque scatter media such as biological tissue. I'll discuss the application to congenital cataract treatment at the end. Optical focusing is critical to many applications such as optical imaging, laser cutting, laser surgery, phototherapy, and optical manipulation such as optical tweezing and optogenetics. However, in opaque scatter media such as milk and biological tissue, light is scattered due to the refractive index heterogeneity within this media. Instead of a focal spot, the light intensity inside scatter media looks like this, which we call a speckle pattern. In general, light scattering prevents optical focusing beyond 1 millimeter deep inside biological tissue, which limits all these applications I just talked about to superficial layers. Therefore, it is highly desired to break this optical diffusion limit and focus light deep inside scatter media to extend the operating depths of all these optical technologies. To achieve these goals, our labs and others developed time-reversed ultrasonically encoded optical focusing, or true focusing, to focus light deep inside scatter media. Let me explain the principle of true. Compared with light, ultrasound is much less scattered in tissue due to its long wavelengths. So we first focus ultrasound to a small volume deep inside scatter medium. Then we illuminate a laser beam. Of course, light will be scattered by all these heterogeneities. But a portion of light passing through the ultrasound focus will change its frequency due to the momentum transferred from the ultrasound. These frequency-shifted photons shown in red come from the ultrasound focus, and we call them ultrasound-tagged photons. Imagine if we can detect only these ultrasound-tagged photons and do a time reversal, these photons will trace their trajectories back to the ultrasound focus where they come from. In this way, they form a focus despite scattering. However, in reality, we cannot reverse time. Fortunately, we can do something called optical phase conjugation using this phase conjugate mirror to achieve the equivalent time reversal. Here's more information about optical phase conjugation. This expression represents a wave traveling from left to right. If we do a time reversal, we get a wave traveling from right to left. Now, if we do a phase conjugation by taking the conjugate of the phase, again, we get a wave traveling from right to left. As you can see, phase conjugation is equivalent to time reversal, which can be proved based on this equation. Here's a comparison between a regular mirror and a phase conjugate mirror that achieves optical phase conjugation. A regular mirror would reflect a beam to this direction, while a phase conjugate mirror would reflect a beam back to where it comes from, as if time has been reversed. Using this phase conjugate mirror, we can achieve the equivalent time reversal, so the ultrasound-tagged photons will trace their trajectories back to the ultrasound focus where they come from. In this way, they form a focus despite scattering. One thing we should note is that biological tissue is not only a scatter medium, but also a dynamic scatter medium, where all these light scatters keep moving due to physiological motions such as breathing, heartbeat, and blood flow. Red blood cells are the main fast-moving light scatters. If photons are singly scattered by blood, the speckle correlation time tau c, which quantifies how fast light pattern changes, can be estimated by lambda over flow speed, which is on the order of 1 millisecond. The speckle correlation time is even shorter if photons are multiply scattered by blood. So ideally, we should complete the true focusing procedure within 1 millisecond for in vivo applications. However, previous implementations operate longer than 200 milliseconds. So you can see there's a strong motivation to develop high-speed true focusing systems. Improving the speed of true focusing is equivalent to improving the speed of the phase conjugate mirror. So we need to first understand how we achieve optical phase conjugation in reality. There are two approaches. In one of the analog approaches, we use a reference beam tuned to the same frequency as that of the ultrasound tag light. They interfere and write a hologram inside a photorefractive crystal, in which the refractive index distribution follows the light intensity distribution in the interference pattern. Then we use another reference beam to illuminate the crystal, and the diffracted light would be phase conjugate to the ultrasound tag light, so the diffracted light would converge to the ultrasound focus. Based on this principle, we developed high-speed optical phase conjugation and true focusing using a fast-responding photorefractive crystal called SPIE crystal, which is made of tellurium-doped tin-silicon hybridiphosphate. During the experiments, we moved our scattering medium to create these time-varying speckle patterns to mimic the dynamic nature of speckles within living tissue. These images show that we achieved optical phase conjugation when the sample is static and also when the sample moves fast, corresponding to a speckle correlation time of 5.6 milliseconds. Using this crystal, we also demonstrated true focusing enabled imaging inside the dynamic scatter medium with a speckle correlation time of 5.6 milliseconds. We embedded an absorptive object in between the two scattering medium, and we apply ultrasound with this transducer. We probe the sample with a laser beam. A portion of light passing through the ultrasound focus will change its frequency. These frequency-shifted photons, shown in red, interfere with a reference beam and write a hologram inside the SPS crystal. Then we use another reference beam to illuminate the SPS crystal, which generates time-reversed light that converge back to the ultrasound focus and further detected by this photodiode. To acquire an image of this object, on this plane containing the object, we scan the true focus across the object and monitor the transmitted light signal by this photodiode. This is the signal we got. You can see when the true focus is on the object, we see a decrease in the transmitted light signal compared with the case when the true focus is away from the object. This is because the object absorbs some of the light. So this dip actually manifests the object, and this curve shows an image of the object. Even when the speckle correlation time is 5.6 milliseconds, we can still acquire an image of the object. As a control, when we shift the ultrasound frequency by 100 kilohertz to destroy the true focus, we cannot see the image anymore. I just talked about how we achieved high-speed true focusing using this fast-responding photoreflective crystal. The drawback of this approach is the reflectivity of the phase conjugate mirror is low, meaning the time-reversed light is much weaker compared with the original ultrasound tag light. To achieve a higher reflectivity, we switch to a digital approach. This approach achieves optical phase conjugation by following its definition. First, we measure the phase of the ultrasound tag light using digital holography. Then we display the conjugate phase on a spatial light modulator, or SLM, that modulates the phase of light. Upon reflection, a planar reference beam acquires this phase and becomes phase conjugate to the ultrasound tag light, so the modulated light would converge to the ultrasound focus. As you can see, this approach involves two steps. One is wavefront measurement, the other is wavefront modulation. Both steps are slow. First, let's take a look at how we improve the wavefront measurement, which is this part. To measure the wavefront of ultrasound tag light, we need to use interferometry. We cannot use Schack-Hartmann sensors here because they cannot measure the highly distorted wavefront of speckles caused by scattering. To deal with speckles, we use cameras and spatial light modulators with a large pixel count on the order of a million. Phase-shifting holography has been used to measure the wavefront of ultrasound tag light. We step the phase of a reference beam through 4 values and record the corresponding interference patterns. By using 4 interferograms, we can reconstruct the phase of the ultrasound tag light. Heterodyne holography is a variation of phase-shifting holography, where we use a camera to sample the beat between a reference beam and tag light at 4 times the beat frequency. The beat provides a natural phase shift. Again, by recording 4 interferograms, we can reconstruct the phase of the ultrasound tag light using this same equation. The drawback of these two approaches is that we need to record 4 images, so the speed is limited by the low camera frame rate, which is typically less than 400 Hz. So it takes at least 10 milliseconds to just measure the wavefront, which is much longer than the 1 millisecond requirement for achieving true focusing in vivo. Off-axis holography can be faster. However, it sacrifices pixel count by at least 16 times, which degrades the focusing contrast. There's another drawback of previous wavefront measurement methods in true focusing. Suppose we use the heterodyne holography to measure the wavefront of ultrasound tag light. Then the light intensity on each camera pixel can be written as this. We have a DC background and an AC signal. The phase of the ultrasound tag light we want to measure is encoded in the AC signal. We can compute the signal to background ratio, which is the ratio between the AC signal and the DC background. Because the ultrasound tag light is much weaker compared with untag light, this ratio can be as low as 10 to the minus 4th. It means that we have a tiny AC signal on top of a huge DC background. So for conventional cameras, after analog to digital conversion, most bits of a pixel value have to be used to represent this informationless DC background, while only a few bits can be used to represent this useful AC signal. This is low efficiency in the use of bits. Also, a conventional camera transfers data corresponding to both DC background and AC signal to a computer. It actually transfers lots of useless data corresponding to the DC background. This can reduce the data transfer speed. It is much better to filter out the DC background first and record only the AC signal with a low-resolution analog to digital converter. This can increase the bit efficiency, eliminate the need of a costly high-resolution analog to digital converter, reduce the data transfer load, and increase the data transfer speed. After investigation, we found the lock-in camera can do exactly this. Let me first review the principle of lock-in detection. Suppose we have a signal buried in a background of other frequencies. The goal is to measure the phase and amplitude of the signal. After passing through this lock-in circuitry composed of local oscillators, mixers, and low-pass filters, we get two numbers, which is the in-phase and quadrature signal. From them, we can reconstruct the amplitude and phase of the target signal. A lock-in camera is a camera in which each pixel is an analog lock-in detector. The camera we use has 300 by 300 pixels and a frame rate of 3,800 frames per second. Here are the advantages of using a lock-in camera in true focusing. First, it is much faster to obtain a phase map. The measurement takes less than 0.3 milliseconds, and we record only one frame as opposed to 4 frames used in previous methods. Second, because we digitize only the AC signal after rejecting the DC background, we increase the bit efficiency, eliminate the need of a costly high-resolution analog to digital converter, reduce the data transfer load, and increase the data transfer speed. First, we use this camera to measure some standard wavefront. Here, we use the camera to measure the wavefront of this plane wave at oblique incidence. We use a reference beam to beat with the sample beam at 70 kilohertz, and we let the camera lock into this beat frequency so we can measure the phase of light. This is the result we got, and it corresponds to the wavefront of a plane wave at oblique incidence. Then we use the camera to measure this spherical wavefront created by this lens, and this is the result we got. You can see the concentric rings corresponding to a spherical wavefront. In all experiments, wavefront was obtained from a single frame taken within 0.3 milliseconds. Then we use the lock-in camera to achieve high-speed true focusing inside the scatter medium. First, we measure the wavefront of the ultrasound tag light, and this is the wavefront we measured. If I zoom in, you can see the wavefront is highly distorted due to scattering. Our method can measure much more complex wavefront than Shack-Hartman sensors do. To achieve optical phase conjugation, we display the conjugate of this phase map on a spatial light modulator. Upon reflection, a planar reference beam will acquire this phase and become phase conjugate to the ultrasound tag light, so the modulated light would converge to the ultrasound focus. To observe the focus, we place a camera sensor on this plane, and this is the focus we observed. As a control, without using our technique, we can now see a focus. I just talked about how we improve the wavefront measurement by using a lock-in camera. Now let's talk about how we improve the wavefront modulation, which is this part. Here's a comparison of different wavefront spatial modulators used for wavefront modulation. Pneumatic liquid crystals are most popular, based spatial modulators are most popular. However, they are slow. They usually take tenths of milliseconds to modulate phase, which is much longer than the 1 millisecond requirement for achieving true focusing in vivo. Digital micromirror devices can be faster. However, they normally achieve binary amplitude modulation, which results in a low focusing efficiency and contrast. We quantify the focusing contrast by focus to background ratio, which is the intensity ratio between the focus and background. In our work, we use ferroelectric liquid crystals as a fast spatial modulator. These molecules can respond to external electric field very fast because of their spontaneous polarizations. The SLM has the shortest runtime of 1 millisecond, including data transfer time. However, unlike pneumatic liquid crystals that can do binary full-phase modulation, ferroelectric liquid crystals can do only binary phase modulation. Fortunately, we can prove, and I will explain in the next slide, that this binary phase modulation scheme only reduced the focusing contrast by around half. However, we gain more than 10 times in speed. Here's an illustration of different wavefront modulation schemes for light focusing using the 3 types of devices I just talked about. Suppose we want to focus light to this target location within a scatter medium. Different beamlets reaches this target location with a different path length and thus phase. The electric field of each beamlet at this target location can be represented by a phasor. And the net electric field at this target location is the summation of all the phasors. Because of scattering, this is random phasor sum. That's why we see a speckle pattern. With a spatial light modulator, we can adjust the phase of each beamlet to make them constructively interfere at the target location, thus achieving a focus. Specifically, with full-phase modulation achieved by pneumatic liquid crystals, we can rotate each phasor to make them constructively interfere. In this case, we can maximize the electric field amplitude and achieve a focus. With binary phase modulation achieved by ferroelectric liquid crystals, we can rotate each phasor by 0 or 180 degrees. So for these phasors that directly interfere with the preceding phasor, we just rotated 180 degrees to make them constructively interfere. Similar for this one, we rotated 180 degrees to make them constructively interfere. Again, we can increase the electric field amplitude and achieve a focus. With binary amplitude modulation achieved by DMDs, we can turn on or turn off each phasor. So we can just turn off those bad phasors that destructively interfere with the rest of the phasors. Again, we can increase the electric field amplitude and achieve a focus. However, this method is less effective than the binary phase modulation scheme. Now that we use these ferroelectric liquid crystals that achieve binary phase modulation, we don't need to measure the wavefront very accurately. So we develop a binary wavefront measurement method that works perfectly with binary phase modulation while doubling the wavefront measurement speed. Due to time constraint, please check our papers for more details. Using this binary phase modulation, measurement and modulation scheme and an optimized system, we achieve the fastest digital wavefront shaping, and we focus light through 3 mm thick moving chicken tissue. Here are the foci we achieved at different speckle correlation times. Even when the speckle correlation time is 2 milliseconds, we can still achieve a focus. As a control, without using wavefront shaping, we can now see a focus. We also achieved millisecond true focusing inside the dynamic scatter medium comprising 2 pieces of moving chicken tissue. Here we focus light to this location. To observe this focus, we use a beam splitter to create a copy of the true focus on a camera so we can measure it outside this water tank. These are the foci we achieved at different speckle correlation time. Even when the speckle correlation time is 5 milliseconds, we can still achieve a focus. I just talked about how we improve the speed of optical phase conjugation and true focusing. Now let me talk about how we improve the focusing contrast, which is quantified by focus to background ratio. For example, this focus has a higher focusing contrast compared with this one, which has a higher background. The first method we found that can improve focusing contrast is to achieve full polarization optical phase conjugation. Suppose we use horizontally polarized light to illuminate a scatter medium. Due to scattering, the light coming out of sample can have all kinds of polarizations. However, previous digital optical phase conjugation systems measure and phase conjugate only the horizontal component of the scattered light field, limited by the principle of spatial light modulator. Given that this is not ideal because we lose information. Since an arbitrary polarization can be decomposed into 2 orthogonal polarizations, we use 2 spatial light modulator to phase conjugate light with horizontal and vertical polarizations, thus achieving full polarization optical phase conjugation. These are the foci we achieved through 4 mm thick chicken tissue with either single polarization or full polarization optical phase conjugation. We can see the focus is brighter. Here is a close-up of the regions denoted by the boxes in the first row. Among all the 3 foci, the focus achieved by full polarization optical phase conjugation has a nearly circular shape that more closely resembles the shape of the input focus. So we also improve the phase conjugation fidelity because we use more information of the scattered light. The second approach we found can improve the focusing contrast and signal-to-noise ratio is by sub-Nyquist sampling the speckle grains during wavefront measurement. Previously, in the optical phase conjugation field, people use more than 2 by 2 camera pixels to sample 1 speckle grain. In this case, the focusing contrast is limited by the number of speckle grains recorded, which is smaller than the pixel count of a phase conjugate mirror. We found that by using 1 camera pixel to sample 1 or multiple speckle grains, we can improve the focusing contrast and the signal-to-noise ratio. The improved focusing contrast is because we have more degrees of control in this phase map compared with this one. Using this technique, we improve the focusing contrast of true focusing in between 2 diffusers. Again, we use a beam splitter to create a copy of the true focus on the camera. These are the foci we achieved with well-sampled wavefront and with undersampled wavefront. You can see the focus, the background is cleaner in this case, and the focusing contrast has been improved. Using this technique and an improved system, we demonstrated light focusing through centimeter-thick scatter media by optical phase conjugation. This photo shows 2 chicken breast tissue samples with a thickness of 25 and 20 millimeter. These images show that we can focus light through chicken breast tissue sample with thickness ranging from 5 millimeter to 25 millimeter. Actually, 25 millimeter is not our limit because we use a green laser to achieve these results. To minimize the light absorption by blood, we switch to use intralipid as a scatter medium, which looks like milk. At 532 nanometer, it is same absorbing as chicken tissue at a near-infrared wavelength, but more scattering than chicken. This photo shows 2 intralipid phantoms we make with a thickness of 96 and 85 millimeter. You can see our sample is even thicker than a human arm. These images show that we can focus light through intralipid phantoms with thickness ranging from 8 millimeter to 96 millimeter. Having discussed about technology development, now let me talk about 2 potential applications of true focusing. The first is optogenetics, where scientists use light to excite neurons to study their functions. However, because the brain scatters light strongly, people have to insert a fiber into the brain to deliver light. This approach is not only invasive, but also has a poor spatial resolution, meaning it cannot target individual neurons. In addition, the use of a fiber makes it inconvenient to excite neurons at different locations. We show that we can use true focusing to focus light non-invasively through highly scattering brain slices. These images show the light intensity distribution through living brain slices of different thickness with and without using true focusing. Compared with conventional focusing, true focusing maintains a focal spot size of 30 micron, even through 2 millimeter thick brain slices. We can use this focal spot to do optogenetics, meaning to excite neurons. We use this electrode to monitor the response of neurons to light as a validation of our approach. With true focusing, we can concentrate more light onto a neuron and induce a larger photocurrent compared with no wavefront shaping case. Also, we can excite neurons with 4 times better spatial resolution than conventional focusing in 800 micron thick brain slices. The second potential application of true focusing is congenital cataract treatment. This photo shows a normal eye and an eye with a cataract. The lens in a normal eye images an object onto a retina so we can see the object. However, if the lens is opaque due to scattering, there will not be a clear image on the retina, so we cannot see clearly. In fact, cataract causes half of blindness worldwide. Although cataract can be removed in humans, we think true focusing may be helpful for congenital cataract treatment, and this project is in collaboration with doctors at UCSF. Congenital cataract is a disease that occurs 1 in every 2,500 live births. Normal development of the visual pathways in the brains of infants relies on clear images being projected onto the retina, which can be disrupted by lens opacity caused by congenital cataract. This disruption, if uncorrected in early life, results in amblyopia, which is permanently decreased vision even after removal of the cataract. To prevent amblyopia, doctors need to remove the cataract during first several weeks of life. However, because the eyes are not fully developed at this stage, the cataract removal surgery risks a host of complications that can even cause vision loss. Research has shown that the risk of one major complication can be reduced 8-fold by delaying the surgery until 4 months of life. We propose to use true focusing to focus light non-invasively through the cataractous lens to stimulate the retina, thereby preventing amblyopia. This approach would allow the cataract removal surgery to be delayed and hence greatly reduce the risk of complications from early surgery. This photo shows the cataractous lens sample we used from a donor. It has a scattering mean-free path of 32 inverse millimeter, so a thickness of 3.5 millimeter corresponding to more than 100 mean-free paths in thickness. Because of strong scattering, we can now see the letters underneath. We built a reflection mode, iterative true focusing system to focus light non-invasively through the cataractous lens to stimulate the retina. This is a schematic of the setup. By using this phase map to correct for the scattering caused by the cataractous lens, we can focus light onto the retina. As a control, without using our technique, light is scattered everywhere. In summary, optical focusing is critical to optical imaging, manipulation, and therapy. However, light scattering prevents optical focusing beyond 1 millimeter deep inside biological tissue. To break this optical diffusion limit, we developed guide-star-assisted optical phase conjugation techniques, such as true focusing and trap focusing. I don't have time to talk about trap today, which is a very powerful technique. For in vivo applications, we developed high-speed true focusing systems based on a fast-responding SPS crystal, a locking camera, a ferroelectric liquid crystal-based spatial modulator, and a binary wavefront measurement method. We also used the locking camera to improve the bit efficiency during wavefront measurement in true focusing. We developed a full polarization optical phase conjugation system that doubles the focusing contrast and improves the phase conjugation fidelity. We discovered that undersampling speckle grains can improve the focusing contrast and the signal-to-noise ratio. We focused 532 nanometer light through tissue mimicking phantoms up to 96 millimeter thick and through chicken breast tissue sample up to 25 millimeter thick. We apply true focusing to congenital cataract treatment and non-invasive optogenetics. The speed and contrast of true focusing need to be further improved for in vivo applications. I would like to thank my advisors, my co-authors, my lab members, and the funding from NIH. That's all. Thank you for your attention.